Welcome back, students. In this video segment, we're going to take a look at section 15.2 entitled Double Integrals over General Regions. All right, let's get started. In order to look at this section, we really kind of need to put the section in the context of picking up directly where we left off in 15.1. So I'm going to need to talk about a little bit about what we did in 15.1 for maybe 5 minutes or so to sort of segue into our new stuff. So in 15.1, we look at the definition of the double integral, and then we look at how we evaluate double integrals over rectangles. Okay. And I want to review that with you because that's where we're going to pick up on this section. So just as a brief review, let me do this again. As a brief review, oops, try this one more time. Okay, so here's our first octant in 3 space, and I'm going to put a surface in 3 space. And we're interested in the region and in the volume of the region bounded above by a surface z equals f of xy, and below by the rectangle r equals ab cross cd. And if you recall, what we did is we first looked at what the graph of the region looks like. So I'm going to try to get that done in some short order time here. So here's x equals a, here's x equals b, okay, here's y equals c, here's y equals d, we'll put it right about there, and here is the rectangle in the first quadrant of the xy plane, and above that rectangle we have our function z equals f of x and y. So let me try to get a decent graph of a surface. Again, I'm going to try to place the surface high enough so it doesn't get in our way near the xy plane. And we have to draw some more stuff. So here's our surface, sort of a lopsided loaf of bread. And the way I explained the process of simplifying the double integral of f of xy over this rectangle was to consider this as a loaf of bread, then slicing through the bread with our knife parallel to the yz plane, and forming a slice of bread. Okay, so there's the slice of bread, and then finding the area of that slice of bread. Now notice on the top of on the surface itself, we see the top of the slice of bread forms a curve, and the equation of that curve is z equals f of x held fixed, x is held fixed, y. So it's really z equals a function of y, where x is held fixed. So we then notice that the area of the slice of bread, not the volume of the slice, just the area of the face of the bread, is equal to, just from Calc 1, the integral from c to d of f, notice I left the x out of there, f of y dy. The function, again, the top of that slice, the top of the curve on the slice of bread is a function of y only because x is held fixed. So I'm going to put x into the function. So we integrate this with respect to y, holding x fixed. Then we gave the bread some thickness. We again slice at a position x plus a little bit of an increase in x, and now we see a 3-dimensional slice of bread. The width of the slice of bread is dx. The area of the slice of bread is the integral of the function dy from c to d. So the volume of the slice the volume of the slice, just using geometry, not even calculus here. It's the area of the face of the bread. And in our terms, that slice of bread forms a cylinder. Believe it or not, a cylinder. If you lay the bread flat, the area of the base is the area of the face of the cylinder, and it has a constant height, if you will, dx. So the volume of the slice is the area of the slice times the height, if you will, of the slice. Okay? So that quantity equals the integral from c to d of f of x, y, dy. That's the area of the slice times the thickness of the slice. So we wanted the total volume. Okay, again, this is just a recap of what we talked about in our last video segment. So the total volume we get by adding up the volumes of all the slices of bread. Okay, that is, we add up all the areas of the slices times dx as x ranges. As we look at all the slices in the x direction, x ranges from a to b. That is, we integrate this expression from a to b. We integrate what expression? We integrate the integral from c to d of f of xy dy, and then integrate that quantity with respect to x from a to b. Okay. The other point of view from this would be that if we sliced the loaf of bread while holding y held fixed, then the volume would be the integral from a to b of f of x, y with respect to x. I'm interchanging the order in which I integrate this. That's what happens when we interchange the orientation of the knife to now be parallel to the xz plane. Okay, and both of these expressions, which we call iterated integrals equal the double integral. Okay, so our result is that the integral, or was that the integral over the rectangle R, the double integral over the rectangle R of f of xy dA, that very complicated thing that we defined using double Riemann sums and such, can be simplified to one of the two iterated integrals, integrating from a to b after integrating from c to d, dy dx, or the equivalent expression integrating with respect to x first. Okay. Now, I want to make an observation here that we didn't make last time, that we could have completely determined the limits of integration by simply looking at the rectangle in the xy plane. We could have determined these limits of integration not by looking at the entire surface, but only looking at the rectangle in the xy plane. Let me see if I can draw a rectangle nicely here. Let's see. Oops. I guess I'm not going to be so lucky here. Okay, so let's do this. Wait a second. I'm trying to get fancy here. I'm trying to draw a rectangle without having to draw it real sloppily. So here's a rectangle. So we, as I was about to say before I interrupted myself, if we're interested in finding the volume of the surface of the solid, we don't have to look at the entire loaf of bread. All we have to do is look at really the rectangle in the xy plane, below which our volume lies. Okay, AB, CD, and this is going to seem like maybe a kind of a wordy way of, a complicated way of doing something that seems real simple, but this, I think you'll appreciate what I'm doing now in our next discussion. We could get set up the integrals by first deciding if we want to integrate first with respect to y, and then maybe draw one line through your rectangle. Draw one line through your rectangle. That line is in the y direction. Okay, that line is in the y direction. So that line tells you how to set up the limits of integration. We're going to integrate first with respect to y. And notice then that the line travels, if you go from south to north, if you go in the direction of increasing y varies from C to D. So when you draw that line through your region in the direction that you're going to integrate first, notice that the line first touches y equals C. That determines your lower limit of integration, then hits y equals D. And then we integrate that result from A to B in the x direction. Okay, if that didn't make sense, suppose we wanted to set up the integral integrating first with respect to x. To do that, we would consider, okay, I'm changing the color of my lines now, putting a line through the region in the x direction. Okay, that x direction is the direction, it is the variable with respect to which I'm going to integrate first. So if I want to integrate first with respect to x, I draw my line through the region in the x direction. And notice that the line first hits the rectangle at x equals a, then last hits the rectangle, passes through the rectangle, hits the rectangle at x equals b, and then we integrate that result as y ranges from C to D. Okay, so on to our topic for today. Our topic for today, as indicated by the title of the section, is to integrate over general regions in the xy plane. By integrating over general regions in the xy plane, I mean we're not necessarily integrating over a rectangle R in the xy plane. So let's see. So what are we going to be integrating over? Well, let's assume that we're looking at the double integral of the function f of xy dA over a new type of region, say D in the xy plane. Okay, and let's say that D looks like this, where D equals the set of all x and y, oh no, here we are, equals the set of all x and y, or xy's. Oh my goodness. My surface is now converting everything that I draw into some sort of shape. Oh, there. Oh, we got rid of that. Okay. Set of all xy such that x lies between a and b, just like before. In the rectangle, x was between a and b. But the y values don't vary between c and d. The lower and upper part of our rectangle pictured above are now curves. So let's assume that the y values now vary between two curves, g1 of x and g2 of x. This region, D, we're going to even be more specific about what we call it. We're going to call it a D Roman numeral 1 region. And what does it look like? It looks sort of like a rectangle that was made wavy. That didn't seem to make too much sense. So instead of the constant D on top, we have a curve on top, a non-constant curve on top. And on the bottom, we have a different curve where x is still ranging between two constants a and b. So this is what I meant by we're sort of now looking at a wavy rectangle. And this is the region over which we're integrating. Okay, if this doesn't make sense, I'm going to draw this in 3D when I go through the method. Okay, so we're still looking for volume, but the base of our region now is not a rectangle. It's this sort of wavy rectangle, if you will, for lack of a better term for the moment. So I want to draw this in 3 space. I want to draw this surface in 3 space. So x still ranges, give me a second here. X still ranges between A and B. So here's x equals A. Here's x equals B. But the lower and upper portions, if you will, of the rectangle are now replaced with curves. So here is the base. This is in the xy plane now. Here is the base. Let me see if I can draw this a little more general on top. Here is the base of our solid in the xy plane. So now let's actually draw this wavy loaf of bread, if you will. I'm going to attempt to draw this solid. I'm going to go up to the solid, and here's the solid, or here's the surface above us now. Okay. The way I've drawn it, it doesn't look like the surface is directly above this this region in the xy plane. So you'll have to use your imagination a little bit. I think there might be a couple of nice drawings in our textbook too, if this doesn't work for us. So we're going to use the same method that we did before. That is a method of slicing through this wavy loaf of bread. So let's imagine taking a knife, and just like we did before, and slicing it through the surface, holding x fixed. I'll use the same red knife as I did before. Let's slice through the surface at some x value. The knife hits the loaf of bread here, goes through, forms a slice. This is where I might have to change my solid a little bit. Comes up. Ooh, let me see if I can clean this up a bit. Let me see if I can clean this up a lot. Okay, I might push my slice over a little bit. Let's see. Bear with me here, folks. I can always zoom forward a few seconds here. Let me slice over here. This might work better. Here, I get past that little bulge over there. Go up to the surface again. Here, go up to the surface. That's sort of cheating a little bit, but that works. Okay. Here's our slice. One slice at x. Increase x by a little bit. X plus dx. Slice through again. Pass the knife through again. Through here. Then we see a 3-dimensional slice of bread. Okay, just before. The only difference is that the base of our loaf of bread is not a rectangle anymore. It's this wavy base, this wavy rectangle, if you will. And just as before, we find the area of the slice, and this is where things get a little different. The area of the slice is the area underneath. It's the area underneath the surface f of x, y. Integrate with respect to y. We've cut the surface so that we can place the curve of intersection in the yz plane. So we integrate with respect to y, but the limits of integration change now. The lower limit of integration is not constant through this region. The lower limit of integration, if you will, is y equals g1 of x. So the lower limit of integration is a function of where we decide to slice at x. The upper limit of integration also is not constant. The upper limit of integration is y equals g2 of x. Okay. The rest of the integral is the same. We multiply by dx to get the volume of the slice. The volume of the slice. We multiply the area of the slice by dx. Then get the total volume by integrating that quantity as x ranges from a to b. But the integral looks different than before. The integral that we're looking at, I'm going to put this down below here, the integral for the total volume then is the integral from a to b of the area of the slice, the integral from g1 of x to g2 of x of f of x, y, integrate with respect to y, and then with respect to x. Okay, that's a big leap from our first integral in the last section over a rectangle. In fact, I'll let you know now that this is one of the first places in dealing with the concept of multiple integration that students tend to have a lot of difficult time with, is these variable limits of integration. I'm going to try to make that as easy as possible. Now, to get these limits of integration, we did not have to sketch the region in 3-space. We only have to look at the two-dimensional projection of our region in the xy plane. That is the base of our solid. Okay, so let me get that base. Here's the base of our solid. It's called a D1 region. We're looking for x ranging between a and b, but we have a function on top, a non-constant function on top and a non-constant function on the bottom. Okay, to get the limits of integration, what I recommend is that you draw a line through the region in the direction of the variable that you're integrating first with respect to, the innermost variable of integration. Okay, so we integrate first with respect to y, and it's the fact that we're first integrating with respect to y that we draw the green line through our region. And as that green line passes through the region from below to above, it first hits g1 of x, and upon leaving the region, it hits g2 of x. Then the last integral, or the second integral in this iterated integral, goes between the two extremes in the x direction. X goes from a to b. The last two limits of integration are going to be constants, always. The innermost limits of integration may be non-constant functions of x, depending on what our region looks like. If we're integrating over a rectangle, the g1 is c and the g2 is d, and so our limits will be constant. But in general, our limits can be variable. Okay. So before we look at a specific example, I want to consider the other type of region that can occur in this section. In this section, this particular region of integration is a type Roman numeral 1 region, or D Roman numeral 1 region. We could also have in this section a type 2 Roman numeral 2 region. The type Roman numeral 2 region is very easy to describe once we have the Roman 1 region. The type Roman numeral 2 region has the y values varying between two constants, c and d, but the x values are non-constant functions. So x could be some non-constant function of y, and y could be x could also be some other non-constant function of y on the right-hand side. So the type Roman numeral 2 region would look like a set of all xy's such that Now, x is not varying between two constants a and b. X varies between one function of y, we'll call h sub 1 of y, and h sub 2 of y, where y varies between two constants c and d. So to get the limits of integration set up for this double integral, for the double integral of the function over a type 2 region, Roman numeral 2 region, maybe draw a line through the region first in the x direction, which is corresponding to the idea that we're going to first integrate with respect to x. We're essentially flipping the limits of integration like we did with the rectangular case, but it's not so simply as just flipping the limits of integration. In fact, it rarely works to just flip the limits of integration when you're not integrating over a rectangle. In fact, it never works if you're not integrating over a rectangle. So x varies from the first function that we hit as the line passes through from left to right. The line first hits h1 of y, then passes through the region at h2 of y. So the limits of integration, the innermost limits of integration, are functions of y. Then, just as before when we had the rectangle, we integrate finally between the extremes in the y direction of our region. Y goes from c to d. Okay, and this is for a type 2, Roman numeral 2 region. Okay. In terms of theory, that's enough for this section. We're going to look at now evaluating some double integrals and see how this plays out in practice. So, my first example for you looks like this. Example. We want to find the volume. So the example is to find the volume of the solid bounded above by z equals 3 minus x minus y. Do you remember what that surface looks like? All the variables are to the first power. It's not a fancy surface. What is it? It's a plane. Okay, so our region is bounded above by a plane and below by d equals the set of all x, y, such that x varies between 0 and 1, but y varies between 0 and the curve line, y equals x. So this is not a rectangle. If I had y varying between 0 and 1, it would be a rectangle, or 0 and 5, it would be a rectangle. But y is varying between 0 and another function, a simple function, y equals x, but a function nonetheless. Okay? We could completely get away with setting up the integral for volume by just looking at the region D. I'm going to show you that, but I want you to see this region drawn in perspective in 3 space. Okay, so let's do the first thing. Let's do this as without a graph of the region. Many times we need the graph of the region to help us out, but let's do this first without the graph of the region. So here's the region in 3 space. Here's the region D in 2 space. So x is varying between 0 and 1, y is varying between 0 and x. Here's y equals x. Here's x equals 1. So our region, the region over which we're integrating, is the triangle in the xy plane where it has x varying between 0 and 1, and y varying between 0 and the line y equals x. So let's suppose we want to treat this as a type Roman numeral 1 region, type 1 region. That means we're looking to interpret this region as a function of x on the bottom, a function of x on top, between two constants. In this case, the constants are x between 0 and 1. So the volume of this region is the definition. It's the double integral over the region D of whatever the surface is on top, 3 minus x minus y dA. That's the volume. And this integral is not an iterated integral. It's a very complicated creature that is a limit of a double Riemann sum. Real complicated thing. But from our theory just a few minutes ago, we can replace this with an iterated integral. If I'm treating this as a Roman numeral 1 region, I have a function on the bottom, function on the top. Imagine drawing a little green line, or not imagine it, just actually do it. A little green line through the region in the direction in which I'm going to integrate first. Okay, and then set up that innermost integral. The integral, the little green line, if we look from, as it passes through the curve from below to above, first hits y equals 0. Then it passes through the region at y equals x of 3 minus x minus y with respect to y. And then x varies between two constants, 0 and 1. Okay, we're going to evaluate that integral. We're going to evaluate that integral in a few minutes. But I want to see this region in 3 space. The fact is, we're going to be generalizing this idea of double integrals to triple integrals, where in the triple integral case, we can't always get away with reducing the setup of the integral to just looking at something in 2 space. We have to be able to draw things in 3 space. So let's do that. Let's take a look at drawing this actual region in 3 space. Okay. So the first thing, we're going to need some axes in 3 space. So here's 3 space. Here's our first octant, where we spend most of our time in lectures in the first octant. And let's graph z equals 3 minus x minus y. Okay. To graph a line, or rather to graph a plane, and again, this is a plane, especially planes that don't pass through the origin, recall that a convenient way of doing that is very often to graph the intercepts of the plane. So let's see where this plane passes through the different axes. Suppose I let y and z equal 0. That means I'm interested in where the plane hits the x-axis. If y and z are equal to 0, then x equals 3. 1, 2, 3. And similarly, if x and z equals 0, y equals 3. 2, 3. If x and y equals 0, I'm just putting these numbers into the equation. Z equals 3 minus x minus y. If x and y equals 0, z equals 3. The z-intercept is 3. Okay, so this is kind of a real simple plane here on purpose. So connect the intercepts. Half of the plane, simply connect the intercepts, and there we go. There's our simple graph of the plane in the first octant. Okay, well, it gets a little rough now because we need to draw only that portion of the region whose volume we're interested in. So notice that in the region in the xy plane, just above this 3D drawing, is a rectangle where the x value goes from constant 0 to constant 1. So I'm gonna slice through this plane at x equals 1. If I slice through the plane at x equals 1, I'm going to see a triangle. I'm going to see this triangle formed. Okay. So here is where, right here in the xy plane, that's where y equals x. Look up at the graph in 2D. This is where y equals x hits x equals 1. So if y equals x and x equals 1, that means y equals 1 also. So this little dot in the xy plane is where the region D hits its maximum value. So if I draw a little line y equals x through the origin in 3 space, just that portion that I need, here's our region D in the xy plane. Kind of shaded it off. Okay. Well, we still need to get the rest of this region drawn in 3 space. So what I'm going to do from the point, that little dot, I'm going to go up to my surface, and that z value where that little dot ends, let's see if I can draw a little more vertically. That little dot that I'm about to get better drawn for us. Okay. Let's see if I can do this. Here we go. Right there. That little dot is on part of our surface. Connect that dot with the z-intercept of our plane above. That gives us the top of our region. The top of our region, I'm shading off now, looks like this. It's only that portion of the plane that's above the rectangle D in the xy plane. So to maybe help you visualize what's this, if you're not able to see from my drawing, our region is a prism. It's a little bit of a prism whose top is the plane z equals 3 minus x minus y, and the base is the triangle in the xy plane that defines our region D. Okay, so just to make sure we're on the same page, in red, here's our region D. So in 3 space, here's our region D. And there you go. Okay. For this particular, good news, bad news, for this particular problem, we didn't need the region in 3 space. And again, the bad news is we're going to need these regions for our own eyes to set up integrals in 3 space, or other triple integrals and so forth. So if we can, occasionally I will actually draw the regions for us to get used to that. All right. All right. So what I'd like to do is to finish up this example, I want to evaluate that integral above. I want to evaluate the integral, the integral which gives us the volume. So I'm going to do that. I'm going to see if my surface will allow me to bring that drawing down here. Maybe not. Maybe if I drag it. I had a student, one of your classmates, show me how to do this, and I forgot. So I'm going to give it my best shot. Okay. Oops. Okay. I'm going to keep dragging this sucker down. No, it didn't work. All right. Okay. Give me a second. Sorry, folks. So I'm going to just write it again and then maybe off the video. I'll do some practicing. Should have done that first. Okay, 3 minus x minus y dA, and that equals the integral. I'm just copying down what I couldn't drag earlier. 0 to x, 3 minus x minus y, first with respect to y, then with respect to x as the iterated integral. Okay. All right, so let's evaluate that integral just for a little practice. First, we're integrating with respect to y, which means we hold x and any function of x in the integral constant. So 3 is constant, and x is constant. So 3 minus x is constant, and the integral of a constant with respect to x is, with respect to y, is that constant 3 minus x times y. Integral of y with respect to y is 1/2 y squared. That is going to be carried as y varies from 0 to x. Then, lastly, I'll integrate that result with respect to x from 0 to 1. Okay, so let's do this. I'm going to substitute y equals x, so 3 minus x times x, minus, I'm going to substitute y equals x again, so 1/2 x squared. There's the evaluation of the antiderivative at x. Then substituting y equals 0, I get no contribution. So I still have, in the iterated integral, to evaluate the integral with respect to x. So very simple Calc 1 integral. So this is the integral from 0 to 1, distributing the x, 3x minus x squared minus 1/2 x squared, integrating with respect to x. Okay, combine like terms, 0 to 1. Combining like terms, I have 3x minus x minus another half x, the minus x squared minus another half x squared gives me minus 3/2 x squared. Integrate that with respect to x. Integral of the antiderivative of 3x and antiderivative of 3x is 3/2 x squared, and antiderivative of 3/2 x squared is 1/2 x cubed. X cubed over 3, cancel the 3. That is carried between x equals 0 and 1. Okay. And if x equals 1, I get 3/2 minus 1/2 x equals 0 gives us no contribution. So there is 1 cubic unit of volume in this region. I don't want to zip off into the next example yet. I want to re-look at this integral, reinterpreting the region D not as a Roman numeral 1 region, but as a Roman numeral 2 region. We just considered this region in the xy plane over which we're integrating D as a Roman numeral 1 region. That means function below us, function of x below, function of x above. Now I want to reinterpret this region as a type Roman numeral 2 region. Now, in order to do that, it'd be a good idea for me to have our region pictured. So let me get a nice quick picture of that. Or at least let me get a quick picture of that. So here's y equals x. Here's x equals 1. Y equals x. X equals 1. I want to reinterpret this region just to practice with setting up limits of integration for double integrals or iterated integrals. A type Roman numeral 2 region has a function of x on the left, and a function of y on the left, and x equals a function of y on the right. So if I want to set up the limits of integration, I imagine drawing a little line through the region first, or rather in the direction of the variable with respect to which I'm integrating first. If I interpret this as a Roman numeral 2 region, I'm going to be integrating our function 3 minus x minus y first with respect to x. As x passes through the region, it first hits x equals y. This is x equals y. And then it hits x equals 1. So we integrate first with respect to x as x varies from y to 1. And then we integrate that result with respect to y as y varies horizontally between two constants. Always the last limits of integration are constants. Y goes from 0 to wherever y is at the peak of this triangle, and we determined earlier that was y equals 1. Heck, we can determine it again. If x equals 1 on the right, then y equals x, so y must also equal 1. Okay. Now, if we evaluate this iterated integral, we'll get the same value. And as you saw in the first section, the order of integration leads to the same value of the integral. The value of the integral doesn't depend on how we interpret the region, what kind of region we interpret it as. But the difficulty can vary depending on the order of integration. As I stated in our lecture in the last section, if we choose, quote unquote, the wrong order of integration for an iterated integral, we may get an integral that's impossible to evaluate. If you don't remember that, it's okay. We have an example coming up that will actually illustrate that. This integral will have a value of 1. I'm not going to evaluate it. If you want to practice with it, that's fine. I want to write out the two iterated integrals that give this volume, though, and I want to compare them before we move on. The volume is equal to the integral of over the region D of 3 minus x minus y dA, the double integral over the region A of the function dA. If we interpret this region as a type Roman numeral 1 region, the integral looks like the integral from 0 to x first, and then with respect to, the integral from 0 to x first with respect to y, and then with respect to x from 0 to 1, or it equals the integral as y varies between 0 and 1, but x varies between y and 1. The reason I want to look at these integrals, these iterated integrals, side by side, is to emphasize that it's not a matter of switching it's not just a matter of switching the limits of integration if we switch the order of integration. Far from. This is considered one of the most difficult skills to acquire in multiple integrals, evaluating multiple integrals by students. Writing out the limits of integration requires a really careful analysis of the region over which we're integrating. It's not a matter, once again, it's not a matter of simply flipping the order of integration. I want to take a look at one more example that will really illustrate that. So I think I got a good example for us. Here's a good example for us. I want to evaluate an iterated integral. And the iterated integral looks like this. It's the integral from 0 to 1, preceded by an integral from 3x to 3 of e to the y squared, first with respect to y, and then with respect to x. Okay? Now, if I wanted to evaluate this, suppose I tried to evaluate this iterated integral without doing anything with the order of integration. I can't. The integral of e to the y squared dy cannot be found using finite combinations of the functions in our universe. This integral has no elementary antiderivative. There is no elementary antiderivative for this integral. Okay, so there is no way I'm going to evaluate this without using some strange techniques. We could probably evaluate this integral by expanding e to the y squared in a Maclaurin series, etc., etc. But that Maclaurin series is going to have an infinite number of terms and stuff. So this is, for us, for all practical purposes, this is impossible. I'll put in quotes. It is really possible, just not easily, just not using functions that we're familiar with. Okay, so imagine, however, if I were integrating e to the y squared first with respect to x. That means I'd be integrating e to the y squared holding e to the y squared constant. Fine. I wouldn't be integrating then a function of y with respect to y. If that doesn't make sense, let's move on with the problem. Sketch the region of integration. That's going to be your mantra, your sort of theme in multiple integration. Sketch the region of integration. The region of integration is a type 1 region. Y varies, if you look at the innermost integral, y varies from 3x to 3. Okay, so let's draw the line y equals 3x. And then let's draw the line, the horizontal line, y equals 3. Let's do this. So 1, 2, 3. So here's y equals 3, horizontal line, y equals 3x. 1, 2, 3. And this is not going to be to a really good scale here. So here's x equals 1. Okay, and then x varies between 0 and 1. So we're integrating over this, the interior of this triangle that we have pictured here. Let me get rid of those little arrows out of there because I kind of need my triangle. Give me a second here. Let's see. There we are. Oops. I think I have to determine when to stop tapping the undo button here. Okay. All right, here we are. Okay, this is good. 1. Okay. So I want to reverse the order of integration. I want to treat this as a type Roman numeral 2 region. That means I want to integrate with respect to x first. The Roman numeral 2 region has x as a function of y on the left, x is a function of y on the right. Okay. You could use the little device I told you about. If we're going to integrate this as, or treat this as a type Roman numeral 2 region, draw a little line through the region in red or some other color than your actual graph is, and then set up your limits of integration as the line passes through the region from left to right. X varies from left. It hits the region at x equals 0. Then hits the right, where I'm marking it off solid here, at x equals y. And then y varies from 0 through the region from 0 to 3. Remember, the outermost limits of integration are always constant. The inner integral, or integrals, as we're going to see with triple integrals and so forth, those integrals may involve functions of variables, okay, non-constant functions. All right, so now let's attempt to, oops. I just noticed I changed my function. The limits of integration may change, but the function doesn't change from a function of y to a function of x. So we're still integrating e to the y squared. Sorry about that. Okay, let's perform this integration. See what happens. Innermost integral first. I'm going to integrate with respect to x holding y constant. E to the y squared is then constant. So I'm going to get x e to the y squared as x varies from 0 to y, and then I'll integrate that result with respect to y. Okay, so let's continue with this. This is the integral from 0 to 3. Substituting x equals y, I get y e to the y squared, a totally simple integral from Calc 2. X equals 0 gives us no contribution. This is not only possible, it's simple. And I think I'm going to have to correct a little mistake here. It's an easy fix. Don't panic. After the first line, I had us going integrating from 0 to y. X doesn't equal y. X equals 1/3 y, and I'm sure a whole bunch of you saw that. So before you write that in the comments below, I'm going to fix it in green. X equals 1/3 y. So I'll fix that here too. 1/3 y. 1/3 y. Sorry about that. So 1/3 y e to the y squared. Better. Okay. This is still a simple Calc 2 integral. It's a u substitution. Let u equal y squared. If u equals y squared, du equals 2y dy. So y dy equals 1/2 du. So maybe do the integration on the side here. So the integral of y e to the y squared with respect to y equals, make the substitution, y dy is 1/2 du. Y squared is u, so it's e to the u. This is 1/2 e to the u plus a constant as an antiderivative, so 1/2 e to the y squared plus a constant. We went from an integral that was impossible to evaluate, e to the y squared, to one that's not only possible, it was simple. The integral of y e to the y squared is simply 1/2 e to the y squared. So that 1/3 will up the value of the integral, or change the value of the integral to, instead of 1/2 e to the y squared, 1/6 e to the y squared. As y varies between 0 and 3, and finish it off. This is 1/6 e to the 3 squared minus e to the 0. Okay, so the order of integration, couple things. Flipping the order of integration doesn't amount to just switching the limits of integration. Compare the two integrals in the beginning of this example in blue. I flipped the limits of integration, but I certainly did not just switch the limits of integration. We need a careful drawing of our region and emphasis on the word careful with my mistake. And the idea here is that the second thing is that flipping the limits of integration can transform our integral from impossible to simple. Okay, not always the case. Sometimes if you flip the order of integration, you still end up with an impossible or a very difficult integral. But occasionally we get some luck out of this. So switching the order of limit integration is very often a good thing. I think that you're going to find a few homework problems that will illustrate this. I have one more example for this section. If you'd like to take a break, this would be a very good time to do so, or you can just continue watching. All right, students, let's finish up this section with an interesting example or an interesting application of the double integral. I'm going to ask the question, what if f of xy equals 1? I'll be much more specific about what I mean by the question. What I mean is, what kind of result do we get from multiple integration, double integration, if the surface is the plane z equals 1? Let's take a look at that. Here's let me draw a particular case of what I'm talking about here. So here's a region D in the xy plane. Okay. And let's assume that we're interested in the volume of the solid above D. Could be type Roman numeral 1, Roman numeral 2, or whatever. But the surface above is z equals 1. So suppose that we're integrating where the surface above is z equals 1. Okay, I might be able to do this a little better. Let's see. Okay. Let's say z equals 1. if z equals 1, then we're looking at the volume of a very specific type of solid. What is the solid that has as a base some arbitrary base, some area in the xy plane, but it always has height 1? It's a cylinder. This is a cylinder of height 1. Well, so what? Well, let's see. So what? Let's see what happens when we look at the integral of f of xy over the region D. Well, f of xy is 1 over the region D. So we're integrating 1 dA, doubly with respect to A. Okay, well, we already discussed that this is a cylinder. This is a volume of a cylinder. Very special cylinder of height 1. What's the volume of a cylinder of height 1? It's the area of the base times the height, 1. This is going to be very interesting if you don't see it yet. It's the area of the base times the height times 1. Well, the area of the base times 1, that's just the area of the base. Oops. That's just the area of the base. The base is D. It's the area of D. So the double integral of 1 just gives you the area of the region over which you're integrating. This is a very different way of looking at areas from Calc 1. Areas from Calc 1, remember, those were the integral of top function minus bottom function dx, or right function minus left function dy. Now it's the double integral of 1 over the region that you're integrating. If that doesn't make sense, let's take a look at our last example. Our last example is to find the area, Calc 1 problem, of the region bounded by y equals x squared and y equals x plus 2. Okay, so just as in Calc 1, we kind of need to look at the graph of our region. So let's take a look at the graph of our region. Okay, so here are our axes. Here's y equals x squared. Here's y equals more of x squared. Here's y equals x plus 2. Y equals x plus 2 is a line with a slope of 1 and a y-intercept of 2. Let's say that's y equals x plus 2. 1, 2. So we're going to have a little problem with scale, but that's okay. Y equals x plus 2. Y equals x squared. So we're interested in the area enclosed by these two curves. But the area is better when you spell area correctly. The area is the double integral over this region of 1 dA. The only thing left for us to do before we dig into the area is to actually finding it numerically is decide if we want to interpret this as type 1 or type 2 Roman numeral true region. We're going to do both. One of them will produce an integral that's nice, quote unquote. One of them will produce an integral that's not so nice. Let's take a look at both. Okay, let's interpret this as a type Roman numeral 1 region first. Type 1. A type Roman numeral 1 region says draw a green line through the region. And the type Roman numeral 1 has a function of x on the bottom, y equals x squared, function of x on top, y equals x plus 2. And green line tells us the direction in which we, or the order in which we put the limits of integration in the innermost integral. So our area then is the integral of 1 with respect to y as y varies between x squared and x plus 2. Remember, we look at the green line as we pass through the region. We first hit the region at x squared. We last hit the region at x plus 2. Then we integrate that result with respect to x between two constants. Just as in Calc 2 or Calc 1, we need to find those left and right-hand endpoints of intersection. And just like in pre-calculus, where you did this first, we'll find the points of intersection by setting the two functions equal to each other. It's a quadratic equation, a real simple one. Factor the quadratic. I'm doing this fairly quickly to not take up too much of our time with the factorization. Simple factorization. So either x equals 2 or x equals -1. Again, my scale is way off here. That's all right. That's okay. So x equals 1. All right. So the limits of integration with respect to x appear as x varies from -1, I think I wrote 1 first, to 2. This is a very simple integral. Let's evaluate it. This is the integral from -1 to 2. Lastly, integral of 1 with respect to y is y as y varies from x squared to x plus 2, and then with respect to x afterwards, substitute y equals x plus 2, substitute x squared. I won't integrate that in this video. This is a very simple integral. Very simple integral. If you're so inclined, you can do it, or you can do the problems in homework, or both. But this value, the value of this simple integral is 9/2 square unit of a square unit. 9/2 square units. Square units. Now, I want to see what happens if I reinterpret my region is a type Roman numeral 2 region. Roman numeral 2, Roman numeral 2 regions are interpreted as regions where we have x as a function of y on the left and x as a function of y on the right. And we have some problems. Look at our region. If we interpret this region as a type Roman numeral 2 region, we have, for a while, the line on the left and the parabola on the right for a while. What do I mean for a while? Look at our drawing. On the left, we have a line. On the right, we have a parabola. However, down near the origin, on the left, we have the parabola. On the right, we have a parabola. So we're going to have to split. If we're going to interpret this as a type Roman numeral 2 region, and we're going to have to split up this answer into two integrals. So let me get rid of my red L and R's. Okay. Now back to our drawing. I'm going to need to split this region into two pieces. I'm going to need to split it where I have that change from one function on the left to another function on the left. Okay, so I'm going to need to integrate, if you will, above that red line and then below the red line separately. So let's do it. Our first integral we got by interpreting the area, the region as a Roman numeral 1 region. I'm putting a subscript in the setup of the integral. So now I want to interpret the region as a type Roman numeral 2 region. So it's still the double integral of 1 dA, but I'm reinterpreting my region as a Roman numeral 2 region. Well, it's a little messy. Back to the drawing. back to the drawing board. So look above the red line. Above the red line, I have the line on the left. If I solve for x, I get x equals y minus 2, and I have the parabola on the right. I have the parabola x equals the square root of y on the right. Now look below the red line. Below the red line, I have a different function on the left than I had before. I have the left branch of the parabola y equals x squared. On that branch, x equals negative square root of y. And on the right-hand side, I have the same right-hand function as I did above the red line, above the horizontal red line. Okay, so this integral is going to look like then. Let's say I integrate below the horizontal red line. Okay, if I do that, I'm going to integrate 1 with respect to x. Now I'll draw a little dotted line through our region. I know it's getting cluttered up in there, but that'll tell us how to set up our limits of integration. X goes from negative square root of y to positive square root of y. Then I integrate that result with respect to y. As y varies from 0 to the horizontal red line. That's 1. How in the world do I know that happens, that occurs at y equals 1? Well, it occurs where x equals negative 1. If x equals negative 1, then if I'm going to stay on the line y equals x plus 2, then y will have to equal negative 1 plus 2, which is 1. So that's how I got that upper limit of integration. Too much coffee. Upper limit of integration of 1. Okay, now that's the portion of this double integral contribution from the below the red horizontal line. Above the horizontal line, red horizontal line, I'm going to integrate 1 with respect to x from the left curve on the left, x equals y minus 2, to the curve on the right, square root of y. And then I'm going to integrate that result with respect to y. As y varies from 1 to wherever y is, we're in the upper portion, at the uppermost portion of our region. Well, at that position, x equals 2. And y must equal x squared, so y must equal 4. Now, compare. No sarcasm intended. I'm going to circle the integral, the iterated integral, and highlight it in green. That's the integral that you would evaluate, the iterated integral that you would evaluate if you interpret this as a type Roman numeral 1 region. And I'm going to circle the integral and re-highlight that integral, the entire integral in red. Those are the iterated integrals that you would evaluate if you interpret this as a Roman numeral 2 region. The bottom line is this. In these cases, when you're deciding whether to interpret your region as a type Roman numeral 1 or type Roman numeral 2 region, you might want to consider the following. If your region has one function of x on the bottom and one function of x on the top, you might want to consider interpreting the region as type Roman numeral 1. If your function has two if your region has two functions of x on the bottom and two or more or one or more functions on top, you might want to consider reinterpreting the region as a type Roman numeral 2 region. Bottom line is this. For a Roman numeral 1 interpretation as your region, it would be nice if you had one function on top and one function on the bottom throughout your region. For Roman numeral 2 region, it would be nice to have one function of y on the left and one curve or one function of y on the right for your region. Okay, and that ends this section, and I'm looking forward to talking with you again soon.